Welcome back. In this video lecture 9.3, we're going to discuss the reading from Chapter 9, Section 4. The title of that section is Collision and Impulse. So collision, the first word, is just telling you what kind of situation we're mostly going to deal with for a while here. Collisions, or more colloquially, crashes. And in fact, pretty much from this point onward in the chapter, things are going to be pretty violent. We're going to have things colliding with other things, crashes of one kind or another. I mean, these things do happen in nature. So how do you apply physics ideas to analyze the motion, predict the outcome of a collision, or whatever? So the first word here, collision, is kind of telling you the situation we're going to be looking at. The second word, impulse, the second main word, impulse, is going to be telling you the new physics, well, it's a hint about the new physics idea we're going to use to study collisions. It's a new physics concept called impulse. Now let me try to give you a little bit of the big picture. In Chapter 7, the key physics concept, really pretty much for the whole chapter, was the work kinetic energy theorem. W net equals delta K. Net work equals change in kinetic energy. And although I didn't go into a lot of the mathematical detail at the time, the way that work kinetic energy theorem is derived is start with Newton's second law in the form F net equals ma, and integrate both sides with respect to position. Say, for example, if it's one-dimensional motion along an x-axis with respect to x. And then the result is W net equals delta K. You want to see that formal proof of that? Physics 310 will show it to you. But that turned out to be useful. W net equals delta K, which then morphed into Chapter 8 into our work energy principle. That was pretty powerful and helpful, and it helped us solve some problems that we wouldn't have been able to solve with Newton's second law alone. So physicists are all about taking an idea that's good, that works, no pun intended, and keeping on using it. So if it was very helpful to integrate both sides of Newton's second law with respect to position, how about integrating both sides of Newton's second law with respect to another important variable in physics, time? That's what we're going to do in this section. And it just turns out that the context in which doing this is most useful is when you have what's called a collision. And really what we mean in physics by a collision is two or more objects interacting with very big forces over very short periods of time. That's what a physicist means by a collision, usually. Two or more objects are interacting, exerting very large forces on each other over a very short period of time. That's kind of what most people often would also think about when you say the word collision. So I have a sketch here on my first slide of an example of what you might mean by a collision in physics. It's a schematic drawing of one moment in time when somebody is taking a baseball bat and hitting a baseball. And the collision, of course, is only that very short period of time when the bat and the ball are in contact. And if we decide to focus, say, on the baseball, then there will be a force on that baseball due to the bat. That's drawn in this sketch. You can see it's this blue arrow labeled F of t, and it's drawn in the plus x direction. Somebody's drawn an x-axis to the right. And that force on the ball due to the bat is probably going to be pretty large, but it's probably going to act only for a very short period of time, and then it's going to be over. No more force. Okay? In fact, if we follow the big blue arrow downward in our drawing, we have a sketch of what that force on the ball due to the bat might look like, plotted versus time. So this F here, what I really ought to denote it as is F sub x. It's the x force on the ball due to the bat. And please note, it's plotted versus time. That's a t. Not x, not position, but time. When we talk about collisions, we're interested in forces acting over a short period of time. Okay? So this purple curve represents the x force on the ball due to the bat as a function of time. Pretty complicated plot. The plot of the force rises up pretty steeply, peaks, and then comes back down. Okay, well, that's just a graph representing the force on the ball due to the bat. Pretty complicated, but short period of time for that force. The force starts at some time t initial, ends at some time t final, so delta t is the duration of that force, probably only going to be a fraction of a second in the case of a bat hitting a ball. Okay, so now we're going to get a new theorem. Just like we had the work kinetic energy theorem in chapter 7, when we integrated both sides of Newton's second law with respect to position, now we're going to integrate both sides of Newton's second law with respect to time and get a new theorem. The starting point for Newton's second law, though, is the new form that we introduced in the previous video lecture. And that one was, we're just writing it now for a particle. This new form of Newton's second law for a particle is that the net force on the particle, that sure sounds like Newton's second law, equals, but instead of ma, we have the derivative of the linear momentum with respect to time. Remember, little p represents the new physics quantity that we introduced in the previous lecture. In fact, one of the most important physics quantities, it's called linear momentum. It's actually more important than acceleration in physics. Remember, linear momentum by definition for a particle is the mass of the particle times its velocity vector. Definitely linear momentum is a vector quantity. So the way to write Newton's second law, more like the way Newton actually said it, is that the net force on the particle equals the derivative of its linear momentum with respect to time, the rate of change of its linear momentum. So that's our starting point for this new theorem. And now we integrate both sides with respect to time. Multiply both sides by dt and integrate both sides. Then you get this expression right here, up to here. The integral of f net dt from t1 to t2. T1 and T2 would be when we would choose the starting time and the ending time. It's going to be based on the context of the problem. If you're interested in, say, a collision between a bat and a ball, T1 is probably going to be the T initial when the collision starts, and T2 is likely to be the T final when the collision ends. On the other side, we've integrated dp dt times dt from T1 to T2. And the way the physicist thinks about this, not the way your calculus professor will think about it, but I think about this dt canceling. It's actually more the fundamental theorem of calculus, and what ends up letting me be left with on the right-hand side is just the integral of dp. Right? Add up a whole bunch of tiny changes in momentum. But now I'm integrating with respect to p, so the limits are momentum values. The lower limit is p1, the linear momentum at the time t1. And the upper limit is p2, the linear momentum at the time t2. And when you integrate up, when you add up a whole bunch of little tiny changes in p, you just get the total change in p between the starting and the ending. That's just delta, finite change in p, and all we mean by that is p2 minus p1, p final minus p initial. So what is this theorem saying? Let me try to get rid of all the stuff I've drawn along the way and just emphasize what it says. It says that if you integrate the net force on a particle with respect to time from some starting time t1, which we will choose based on the problem, to an ending time t2, which we will choose based on the problem, the answer will be the net change in the particle's linear momentum, p2 minus p1, for that time interval. Okay? That's called the impulse linear momentum theorem. Why is it called that? Well, you can see part of that linear momentum theorem because it's got the change in the linear momentum. Where's this impulse part coming from? Well, there's a new definition. We're just going to define a new concept in physics. Not really that necessary, but all the books do it. This new quantity is called impulse. That's its name in physics. Its symbol in physics is a capital J with an arrow on top. Yes, it's a vector. This new quantity called impulse. It's got a magnitude and a direction, or to say it another way, it's got components. And we talk about the impulse associated with a force F acting over a time interval from T1 to T2. And here's the definition of impulse. J arrow. Note the 3 lines. Then he says, hi, everybody. Okay. The definition of impulse, J arrow, is, well, exactly the left side of that new theorem I just talked about. The integral of the net force, or I'm assuming that there's just the one force F, so that's the net force, dt, from T1 to T2. Integrate the force with respect to time. From T1, start, to T2, finish. And remember that an integral is area under a curve. In this case, the curve needs to be F plotted versus T, time. That's exactly what I had sketched over here on the right side. So the impulse is the area under the plot of force versus time. So the impulse is that light purple shaded area with a J in it, in our drawing there, in our sketch, in our plot. Okay? Because impulse is integral of force with respect to time. And an integral is an area under a curve. In this case, you got to plot force versus time. Okay? Now, we really ought to think of it by components because force is a vector. And so the integral of force dt is still a vector, and j is a vector. So really, you ought to talk about the x component of the impulse. And that would be the integral of the x component of the net force dt from T1 to T2. And if there is a y component of the net force, you can talk about a y component of the impulse. Integrate F net y component dt from T1 to T2. Now with that definition of this new quantity called impulse, being defined as the integral of the net force dt, now we are ready to state very succinctly the impulse linear momentum theorem. Remind you what it was up above. Integrate the net force dt from T1 to T2, and that equals the change in the linear momentum. But the integral of the net force dt from T1 to T2 is just what we called impulse. So the succinct statement of the impulse linear momentum theorem is that the impulse on a particle equals the change in its linear momentum. But remember what impulse is by definition, integral of force with respect to time. And again, by components, the x impulse equals the change in the x momentum. And the y impulse on the particle equals the change in the particle's y momentum. So let's just get right into practice using that. What? The impulse linear momentum theorem. That's the that. So I'm going to basically do an interactive exercise with you here. That's what this practice is on the impulse linear momentum theorem. We're going to be going back and forth between some questions here and a Wiley Plus simulation. First, let me describe what's going to be going on in this simulation. We're going to be looking at a particle moving on a horizontal frictionless surface. The particle moves initially in the negative x direction toward a spring of spring constant k. So actually, to sketch over here in the corner what's going on, there's a horizontal frictionless surface that is an x-axis. We've got a particle. It's going to look surprisingly like a box. And it is initially sliding, traveling in the negative x direction. It's got a velocity. And since it's got some mass, m, and velocity v, it will have some initial linear momentum, m times v. It's traveling towards a spring of spring constant little k, with one end of the spring tied fixed to a wall, the other end of the spring free. So we can see what's going to happen. The block's going to keep moving to the left. It's going to come into contact with the spring. It's going to start to compress the spring. That's going to slow it down gradually or smoothly. It will stop for 1 instant in time when the spring is at maximum compression. Then it will speed up, moving back in the plus x direction. It will then leave the spring when the spring is at its relaxed length, as you see here, and then the block will continue moving to the right, plus x direction. That'll be the sequence of events. And the animation is going to show that. The animation is also going to show a whole bunch of graphs, okay? It's going to plot, for example, the net external force on the particle will be due to the spring as a function of time. Okay? Well, net external force as a function of time, area under that will be impulse, right? The area under that plot is the net impulse on the particle due to the spring. It's also going to plot what's called the average force on the particle due to the spring. We're going to talk about why we do that in a minute. And then it's also going to plot the x component of the particle's linear momentum as a function of time. So, okay, with that set up, let's now turn to the animation. Okay, so now you can see the initial situation. The block is traveling in the negative x direction towards the spring. You can see it's going to make some plots for us. Let's go ahead and run the animation. Sure enough, just what we predicted happened. Now note, I'll bring it back. The blue arrow here is the spring force. The force on the block due to the spring while the block is in contact with the spring. What's that kind of orange or gold colored arrow? That's the linear momentum, P arrow. Remember, that's m times velocity, V arrow. Okay, slows, turns around, speeds up, goes back. And let's look at those graphs. The top one, F spring in newtons versus time in seconds. The blue trace is the actual spring force as a function of time. That's a kind of a complicated graph. The area underneath it is shaded light blue. That area, that's the impulse. Look at that. It tells me what the area is, which is convenient because I wouldn't be able to just look at that and tell what the area is. The animation tells me the area under that plot is 10, and the unit is Newton times second. Let's just focus on that for now. And let me go back and now look at the first question. What is the impulse on the particle due to the spring? Use a spring constant little k, by the way, of 1 Newton per meter. That's the default value. So let's write the answer down here. Now, I would like you to pause the video and think about it for a minute, and then come back and we'll talk about the answer. Okay, how are we going to find the impulse on the particle due to the spring? First of all, everything here is, motion is along x, forces are along x, linear momentum is along x, impulse is along x. There's only x components. So I'm going to label this answer as J for impulse, due to spring, x component. Remember, impulse is a vector. Well, by definition, that would be the integral of the spring force, x component, dt. Integrate with respect to time, please, not position x, time. And integrate from t1 to t2. where T1 is when the collision starts, when the block first makes contact with the spring, and T2 is when the collision ends, when the block leaves the spring. Well, I would have to know that actual force function of time to do the integral. Pretty messy. But remember, an integral is an area under a curve. In this case, the curve is spring force versus time of F spring versus T. And the animation, very conveniently, tells me what that area is. 10 Newton times second. So there I'm telling you the x impulse due to the spring on the block. We could, if we wanted to, write this answer in unit vector notation. It doesn't tell me I have to, but let's do it for practice. The impulse vector from the spring on the block is 10 Newton second I hat, right? It's in the plus x direction. That's the answer to question 1. Now let's go on to question 2. If the duration of the particle's contact with the spring is delta t equals 3.2 seconds, what is the, watch this word here, average force on the particle due to the spring in unit vector notation? Give SI unit and give 2 significant figures. All right, I want to go back to the animation and talk a little bit about what they're asking here. Okay, so there's the animation just as we left it. And we note that there are 2 force plots. The force on the left is the actual spring force versus time. That's the blue trace. And it's kind of a complicated shape. The force on the right, notice the vertical axis is labeled FAVG, the average force on the block due to the spring versus time. By definition, the average force is constant. And so that curve in red jumps up and then stays constant during the collision at some constant value for F average and then goes away again. And it does indeed look like the duration of the collision, when the force is not 0, looks like the collision goes from 2 seconds to a little past 5 seconds. So when they tell me that the duration of the collision, delta t, is 3.2 seconds, that sounds reasonable, yes? And what they want me to tell them is that value of the F average graph when it's not 0. How are we supposed to find that? By definition, the constant F average for the collision between block and spring on the red curve, that value of F average is constant is chosen so that the area under the F average curve, the area shaded in red, is equal to the actual area under the actual spring force curve, the area shaded in blue. And you can see it says for the red curve, area equals 10 Newton seconds. You choose the value of F average, or F average is by definition the value such that the area under the red curve equals the area under the blue curve. Okay, so what I want to do is I want to now go back to my notes screen here, and I want to give myself some room here so I can write my answer for question 2. So here's the point. You choose the value of that average force so that it has the same area under it as the actual force. But the area under the actual force was the x impulse due to the spring. So the area under the red curve equals the actual impulse. But the red curve is just a simple flat top. So the area is a rectangle. So the area is the height. That we'll call F average x times the width. The width is the duration of the collision, delta t. In other words, this right here is the area under the plot of f average versus t, the area of that red rectangle. So all we have to do is now solve this equation for f average x. It's the impulse, x impulse, on the block due to the spring, divided by the duration of the collision, delta t. But the x impulse on the block due to the spring is 10 Newton second. And I'm told the duration of the collision is 3.2 seconds. Note the units of seconds are going to cancel. I'm going to be left with a quantity with units of newtons, and that turns out to be 3.125 newtons. If you want to write it in unit vector notation, you would write FAVG arrow equals 3.125 newtons I hat in the plus x direction. I do believe the average spring force during the collision is in the plus x direction. 3.125 newtons. Let's look back at the animation. Look at the average force plot. Look up there at the top where it's flat. Look at the force value there. Yep, it looks like it's just a little bit more than 3 newtons. So this value for the average spring force during the collision seems reasonable. We will often do this, by the way. We will replace the actual plot of the force versus time, in this case the plot on the left in blue, because that's, for a collision, that's usually going to be a pretty complicated plot. And we're going to replace it with the simpler average force, which by definition is constant, with the value of the average force chosen so that the area under that curve has the same area as the original force. And then just deal with the average force. And just ask, what's the average force on our particle during the collision? That will generally be good enough. Now, let's go on to the next question. Question 3. Bring that down just a little more. What is the change in linear momentum of the particle as a result of its interaction with the spring? Change in the linear momentum. That's 3. I will be even more careful and denote it like that. Delta p sub x. It's the change in the x linear momentum, because the motion's along x. And we know the x linear momentum of the block changes. It's initially moving in the negative x direction. It slows, it stops, so p sub x goes to 0 for 1 instant. And then it speeds up in the positive direction, so p sub x is now positive and gets bigger. Once the block leaves the spring, the p sub x is constant. Let's use this new theorem we've got, impulse linear momentum theorem, to get delta p sub x. Because the impulse linear momentum theorem says the change in the x momentum of your particle equals the net x impulse, which for us is coming from the spring. But we know what JSX is in this problem. 10 Newton second. So that's delta px. Now let's just write the units a little bit differently. 10 times Newton kilogram times meter over second squared times second. Note 1 factor of second cancels, and we have 10 kilogram meter per second. That's equivalent to a Newton times a second. If I want to write it in unit vector notation, I can. Delta p arrow would be 10 kilogram meter per second I hat. So that's the change in the linear momentum. It's just equal to the impulse, which we already found. Let's look at the linear momentum plot in the animation. That's the bottom plot, right? P sub x versus t, where P sub x is in kilogram meter per second and t is in seconds. So that's the curve in gold. it sure looks like the initial linear momentum is about -5 kilogram meter per second. That's when the block's traveling in the negative x direction towards the spring. Then starting at t equals 2 seconds, the x momentum goes to 0, and for 1 instant in time, the x momentum is 0. That's when the block is momentarily at rest. And then the x momentum increases in the positive x direction, and then when the block leaves the spring, it's constant again. And it looks like after the collision, the value of p sub x is +5 kilogram meter per second. So what's the change in p sub x? P final minus P initial, 5 minus -5, 10 kilogram meter per second. So our answer for question 3 seems reasonable. All right, let's go on to the next question. Question 4. It's going to have us go back to the animation. It wants us to increase the spring constant to the value k equals 2 Newton per meter. We're going to double the spring constant. We're going to make the spring twice as stiff. We're going to run the animation again, and they're going to ask us which of the following statements is the most accurate. So let's go to the animation and do what it asks. Let's reset. Okay, there we've reset. You can see the second slider lets me adjust the spring constant, so we'll go up to 2 Newton per meter. So the picture doesn't show anything different, but that spring is now twice as stiff as it was. So why don't you just take a moment and predict in your mind's eye, run the animation, predict what you're going to see. Okay, and now we're going to run it. Whoop up. The collision lasted for a much shorter time interval, yes? Maybe just a little more than 2 seconds. Look at the plots, all the plots. F spring, the actual spring force. Ooh, it goes up pretty high now. Still pretty messy. The average spring force, that's a nice flat top rectangle, but it still goes up pretty high. And then the px plot. Okay? Got a picture of that? Now let's go back to the question so we can decide. It was a multiple choice, wasn't it? What's the correct answer? Okay, so what happened when we doubled the spring constant? A. Let's see if this is accurate. Increasing the spring constant K did not increase the impulse on the particle. What do you think? Is that true or false? Increasing the spring constant K did not increase the impulse on the particle. How would you check that with the animation? Did you say, well, the impulse is the area under the plot of the force versus time, whether it's the actual force, that's the plot on the left, or the average force, that's the plot on the right. They have the same area. Did it make that area under those curves bigger? Well, it says there it didn't, right? 10 Newton second. Each plot goes higher, but it's narrower. And in fact, the area is the same. So, it says increasing the spring constant did not increase the impulse on the particle. That's true. Let's hope the others are false, but let's not just stop. Let's think about all those others. B, increasing the spring constant K did not, watch out, not increase the average force on the particle. Can you see why that's false? The average force plot was higher than before. Yes, it definitely made the average force bigger. Increasing the spring constant K increased the duration of the particle's interaction with the spring. Did the collision last longer? No, we already noted it lasted less time. It decreased the duration of the particle's interaction with the spring. False. D, increasing the spring constant K increased the final momentum of the particle. You say why that one's false? Let's make sure we can explain that physically. We already argued that the impulse has not changed. The area under the curve has not changed. The impulse equals delta P. P initial is the same as it was, so P final has to be the same. So increasing the spring constant did not increase the final momentum. Just because the spring was stiffer didn't send the particle out going any faster. That might be a little bit counterintuitive, but it didn't. What the spring increasing, the spring constant did for us is two things. It decreased the duration of the collision, and it increased the average force. Okay? But it did not change the impulse, and it did not change delta P, the change in linear momentum. Okay, that leads us to the last question to consider. Let's imagine that the particle in the animation is a box of delicate equipment reacting with a bumper, the spring, attached to a factory wall. Our goal is to minimize the likelihood of damaging the equipment in the interaction with the spring. Which of the following actions would you recommend to the foreman, the foreperson on the factory floor, if your goal is to not damage the equipment that's in that box when it interacts with that bumper? We've got four things. We have to decide which is the best one. A, minimize the spring constant. We want to pick the right thing to do and the right reason for it too. Minimize the spring constant, which will maximize the interaction time between this box and the spring. Should we do that? B, maximize the spring constant K, which will minimize the interaction time between the box and the spring. Should we do that? C, minimize the spring constant K, which will minimize the change in linear momentum of the box, delta P. D, maximize the spring constant K, which will maximize the change in linear momentum of the box. I want you to pause the video, think about what you would recommend and why, because we want to pick the best answer, okay? All right, so let's give myself a little bit of space here so I can write. Okay, we're answering number 5. Seems to me that my goal is to minimize the effect on the box with its equipment inside. I don't want to have a huge force acting on the box. So what I'm going to do is I'm going to take the impulse momentum theorem average force version. That will be good enough. And I'm going to rearrange it for the average force on the box, the average X force. That's the X impulse over delta T. But from the impulse linear momentum theorem, the X impulse is the change in the X momentum. So I can also write it like that. This change in the X momentum, that's fixed. That's 10, positive 10 kilogram meter per second. Changing the spring constant does not change that. The box goes in with negative 5 kilogram meter per second of momentum, and it goes out with positive 5 kilogram meter per second of momentum. We saw that in the animation when we increased the spring constant from 1 Newton per meter to 2 Newton per meter. So that delta Px is not something that's going to change. But what we can affect by changing the spring constant K is the duration of the collision, delta T, right? That's the duration of the collision of the box with the spring. The spring is that bumper on the wall. If we don't want to damage the equipment, we want to make this force as small as we can get it. So how to do that? Make the duration, delta t, as big as you can get it. Yes? Because it's in the denominator here. Stretch out, no pun intended, the time for the collision. You still have to have a certain delta px, 10 kilogram meter per second. That's got to happen. But if you stretch out the time for it, the duration, delta t, you can make the average force that results on your particle smaller. So your advice to the foreperson in the factory, so as to have a small average force on the box, and therefore the equipment, is to minimize the spring constant K. Right? Because in minimizing the spring constant K, you are maximizing delta T. And that's what you want to do to have the force as small as possible. Let's go back to the animation. Right now what I've got is the biggest K I can have. I've maximized the spring constant, little k, and notice the effect was to make the average force big. So let's go to the other extreme then. Let's reset the animation. Let's make the spring constant as small as we can. Just so happens that in this animation, that's 0.25 Newton per meter. All right? So that's a very weak spring. Let's run the animation. Notice we stretched out the time. It goes from 2 seconds, the collision, to a little past 8. So we've got a lot of time. Therefore, to get our 10 Newton second impulse, 10 Newton second or 10 kilogram meter per second change in momentum, we don't need a very large force. We don't need a very high rectangle there in the force plot. Okay? So that is the idea behind a lot of interesting situations. If you don't want a big force on something, yet you have to have a certain momentum change, stretch out the time for the collision. The demo that we often do when we do our roadshow to the local elementary schools, and we don't do both of these, but what you can do is if you're outside, take a fresh egg and throw it against a brick wall. You have to have a certain change in momentum, the final momentum being 0, the initial momentum being the mass times whatever velocity you gave the egg when you threw it. But you got to have a final momentum of 0. So your delta P is set. You got to have a certain delta P. And if the time of the collision, delta T, is very short, like it would be when an egg hits a wall, the average force on the egg is big. Result, broken egg. Now repeat with another egg, throw it at the same speed, but now throw it at a sheet, a bed sheet that 2 volunteers are holding. And when the egg comes into contact with the bed sheet is pliable and gives a bit. That extends the time of the collision, delta T, and the average force on the egg, therefore, is less. And the egg usually survives uncracked. It's the same idea behind how occasionally, as gruesome as it sounds, when a person does a parachute jump, skydiving, every once in a while, about every 1 in 100,000 drops or jumps, you have a double chute failure, right? The original chute fails and the reserve chute fails. Usually, unfortunately, it's not good, the outcome, because you have a certain change in P, change in linear momentum. Person has a certain velocity V right before reaching the ground, and the final velocity is 0. So there's a certain delta P that has to happen. If the time of the collision is very short, delta T, the F average is going to be big on the body. But every once in a while, and these situations are rare and famous, somebody survives a double chute failure in a skydiving incident. And although the details are not always exactly the same, there's usually the following that's in common. The person falling was lucky enough that during the collision with the ground, they came into contact with something flexible, pliable, malleable, something that gives, not hard ground, concrete, even water. No. Something flexible, a big snowdrift, bushy, big, thick bushes, deep, thick bushes, trees with a lot of foliage. Things that, being flexible, extend the delta t of the collision. Still have to have the same delta p, but if you extend the delta t, then the average force doesn't have to be so big, and the person has a chance of surviving. So physics can explain how those people survive. Something happened to extend the delta t, okay? And that made the force small enough that they usually came away still probably with pretty nasty injuries, but not life-threatening. It's the same reason behind safety helmets on construction sites. You have a hard outer covering, but there's also a kind of a springy layer inside, so that if something does hit your head, okay, the collision with your head, the time gets extended because of the springiness of what's inside the helmet. Okay, so the impulse momentum theorem does help you explain some actual physical scenarios. And then in class, we're going to do an example problem. I'm going to go back to a baseball bat hitting a baseball. Okay? Okay, but that's all for right now, so that's all for this.